we're taking a look at linear combinations of random variables, which maybe is a little bit more highfalutin language than what you need. But we're moving this towards making good decisions, or maybe some tools we might use in financial terms in particular. So we want to look at the shape, center, spread, and the relationship between them. So the first one is that the shape, basically we almost, just for simplicity, we assume that they're normally distributed. And basically it's a multivariate normal distribution, but that's something else. And the linear combinations of these can also be Laurent distributions. So that's the shape. It's going to be normally distributed. The center then is we'll have to take some linear combinations. So the mean of a weight times a particular value plus the mean plus a weight times another particular value will just be the weight times the various means and sum those all up. So let's go ahead and pick up the example that we had previously in terms of the social choice one. What we had was that social choice had a mean of 5.16, 0.29 for stock, 0.45 the global fund, and negative 9.12 for real estate. So it was losing money at the time. So what you do is you take, remember our balance was 0.4, 0.35, 0.15, or 0.10. We plug in the means, and it turns out that we get 1.321. So the portfolio's yield may vary, but it should give us an average about 1.31%. The second one we did already, that we got the mean, and sometimes called an unbiased estimator, and then worked on for that. Now, let's take a little bit of time out for covariance between two variables. So we're going to denote sigma 1 to be the standard deviation of x1 and sigma 2 be the standard deviation of x2, and rho of 1, 2 will be the correlation between x1 and x2. Rho, where have we ever seen that before? Well, you probably have seen rho in terms, now rho is a Greek letter, and then we have the r. You had this some examples. Remember that r goes between negative 1 and 1. If all the points lie on the line, then r is equal to 1. If all the points lie on a line that's negative, then r is equal to negative 1. So it's just a measurement of how two variables are related to each other, anywhere between -1 and 1. Well, we need a little bit more ways of using this. And so what we have then is the covariance. And so the covariance, we're going to represent this as sigma 1, 2. This will be the correlation between 1 and 2 times the standard deviation of the two. Another way you could say that is r is equal to the covariance between the two divided by their respective standard deviations. I don't know if you knew that or not. Did you? That the covariance here is equal to the correlation of x1, x2 times the standard deviation. Another way you could calculate what r is going by that method. So now the thing about the covariance is that it could have any value whatsoever, negative, positive, or 0. Whereas r goes between negative 1 and 1, covariance could be, because you have different scales, it could be 3 million, it could be negative 250,000, it could be 0.3, so it could have any value. And a positive covariance means that the two variables are positively related. So let me show you a possibility of how you could take a look at this. Here we have the mean of y and the mean of x, and so it's positively correlated. Small x values go with small y values, large x values go with large y values. It's negatively correlated and have a negative covariance if you have small x values go with large y values and large x values go with small y values. In other words, there's a downward trend, and so the covariance is negative, just kind of like we have a negative correlation. And then if they're all spread out, you'll have a covariance near 0. And if they covariance of 0 means there's no linear relationship. That doesn't necessarily mean they're independent. If they are independent, then the covariance will equal 0. But it's possible to have a covariance of 0 and not being independent. One thing is that if you subtract all the values of x by a certain number, your covariance is not related. However, if you multiply it by a number, it is multiplied by that constant, which is where we get into some situation. So then what if we take the covariance with itself? So the covariance of a random variable with itself, so let's say we take the covariance of xx, well, what that gives us is sigma x squared. So the covariance of a random variable with itself will be the same, sigma squared. Okay, now let's take a look at the spread. The first time we're going to look at this is we're going to do a situation where we have the values independent and then when they're not independent. So let's take a look at, let's suppose that our random variables are independent. What that means is that the covariance between the two we're going to just assume to be 0. So let's go back to our example with the bonds, stocks, and real estate. Here's my expected return. Let's take a look at the volatility, sigma. And let's take that the volatility for my little bonds, stocks, and real estate will be, let's make it 10%, 25% for stocks, and 20% for real estate. All right. And so if we go ahead and calculate then the variance of our y, because remember our y is we've got 20% in bonds, 70% in stocks, and 10% in real estate, then the variance of y will be 0.2 squared times the variance of bonds plus 0.7 squared times the variance of stocks plus 0.1 squared times the variance of real estate. And so that would be 0.2 squared times 0.1 squared and 0.7 squared times 0.25 squared plus 0.1 squared times 0.2 squared. I mean, we could derive these. We kind of derive them in mathematical statistics. You don't need to know that as much. You could just use the formula. What we end up getting is 0.04 plus 0.1225 plus 0.002, and we get a variance of 0.1285. And this is kind of the first time we see the value of diversification in our portfolio. So we lose a little bit in terms of our expected return. Remember, we only expected a gain of 7.8%, but we've decreased our volatility. If we had put it all in stocks or all in real estate, we'd have a pretty high volatility of 0.25. Actually, that's just the variance. I'll need to find the square root of that. So the square root of 0.1285 turns out that I've got a volatility of 0.35, which is not possible.